Welcome back, friends, once again in another episode of dimension analysis. And before learning uses of dimension analysis, we must know principle of homogeneity. Principle of homogeneity we use while checking the correctness of a equation or relation. And what is the statement of the principle of homogeneity? Let me tell you here. It states that the dimensions of every terms of a physical relation on both sides of the equation must be same. Dimensions of every terms on both sides or on two sides of a correct physical relation. So here's the statement: dimensions of every terms on the two sides of a correct physical relation must be same. That's the principle of homogeneity. So let me take a very simple example of any physical relation. Let's say equation of motion: v square equals to u square plus 2as. Alright, we know very well what does this represent here. V represents final velocity, so it has definitely the dimensional formula lt minus 1. Alright, and u represents the initial velocity. Again, the dimensional formula should be same because it's velocity, and here a represents acceleration, so the dimensional formula of acceleration, that's change in velocity over the time. Alright, or simply you say change in velocity over time, that's lt minus 1 divided by time, so that's gonna be lt minus 2, and s represents here displacement, so the dimensional formula is getting L. And now, according to the principle of homogeneity, dimensions of every terms means this term, and this term on the two sides, so on the left hand side as well as on right hand side, of a correct physical relation. So if it is a correct physical relation, then the dimensions of v square or u square or 2as must be same. Okay, so let's check it out. Velocity has lt minus 1 dimension, lt minus 1, so the square of lt minus 1. Similarly, u has lt minus 1 again, so square, and plus 2as. 2 is a constant, so we don't have the dimension for constant. And acceleration, that is lt minus 2, and this is displacement, so this is just L, so it's going to be now L square t minus 2, and here also L square t minus 2, it's t. Alright, and here also L times L, it's L square and t minus 2. Absolutely correct. We know that v square equals to u square plus 2s. This is a correct physical relationship, and dimensionally also it's proved that this is correct because every term have the same dimension. Alright, so dimensions of every terms on the two sides of a correct physical relation must be same. That's the statement of the principle of homogeneity. Always keep in mind. Let's take one more example, whether it's working or not. Alright, it's a v equals to u plus at. Alright, this is a very correct equation, and I'm writing it little wrong. Alright, v equals to u plus st. So if the principle of homogeneity is stating that every term should have the same dimension, and if we are getting the same dimension, then it is correct, otherwise it's incorrect. It's just a kind of application. Alright, so the v is having dimension lt minus 1, u is also having lt minus 1, and here s means L. Alright, and t means t. Alright, so here t means time actually. So see here, lt minus 1, lt minus 1, lt minus 1 is not here. It means this relationship is not correct. Alright, this is wrong. And if we follow this, then principle of homogeneity also applies very nicely here. This is lt minus 1. Alright, u again lt minus 1. Alright, acceleration, that is lt minus 2. Alright, and this time again. Alright, so overall this makes lt minus 2 plus 1, so it's minus 1. Alright, it is already lt minus 1, and it is again here lt minus 1. So lt minus 1, lt minus 1, lt minus 1. So don't pronounce like lt minus 1, t inverse it is. Alright, t inverse 1. My English is really bad. Anyways, so That's what I'm saying. The principle of homogeneity states that if any correct physical relation is there, then every terms on the both side must have the same dimensions. Alright, that's the principle of homogeneity.